Of this unit that we are going to be focused on is the periodic table and how it came to be. So, the first really prominent person that we're going to talk about in discovery of the periodic table is Dmitry Mendeleev. So, essentially, he took this nice extensive list of elements and he wanted to organize elements by their properties. So, first, he put them in order of increasing atomic mass. So you can see like 9, 11, 12, 14, 16, 19, 24, 27, 28, 31. So elements are listed in order of increasing atomic mass. But what he also did was he grouped elements by similar properties. So you can see like lithium, sodium, potassium, rubidium, fluorine, chlorine, bromine, iodine. So these are groups of elements that are still the same today. Now, the reason his periodic table was noteworthy is because we had these blanks here. So essentially, what he was able to do was figure out, all right, there's an element here, and we haven't discovered it yet. We don't know exactly what it is, but it's going to have a mass that's about 68. It's going to have these types of properties. It's going to have this density. And it's going to fit into my table right here. So although we hadn't discovered it yet, he was able to put in these spaces so that when it was discovered, it should have fallen into place, which they did. Now, about 40 years later, Henry Moseley took these elements and he realized that they fit better into patterns when arranged by increasing nuclear charge. Now, when we think about the charge on a nucleus, we know the nucleus is positive, but why is it positive? Well, the nucleus has protons and neutrons. So protons are my positive part, neutrons are neutral or have a charge of 0. So increasing nuclear charge just means increasing our number of protons. Now, we know today that the number of protons is equal to the atomic number. So this whole theory of putting elements in order of increasing nuclear charge led to the modern definition of atomic number. And we realized that elements arranged by atomic number and not atomic mass put them into groups by similar properties just a little bit better. So according to periodic law, when elements are arranged in increasing atomic number, or by increasing atomic number, elements with similar properties appear at regular intervals. So when we look at our periodic tables, what we're able to see is elements that are in the same column, which is also known as a group or a family, have similar properties. So there's two main groups on our periodic table that are divided by this staircase. So the metals are all on the left of my staircase, where the non-metals are on the right, with the exception of hydrogen. And along my staircase are elements that have properties of both metals and non-metals. And we call those elements either metalloids or semimetals. So now a little bit more in depth here, we're going to look at specific columns on the periodic table, or chunks of columns. So group 1 are my alkali metals, and you can see here that hydrogen is not included in that. Hydrogen is a non-metal, but every other element in this column is an alkali metal. So group 1 of my periodic table, which we just learned is part of my S block, has the most highly reactive metals. Now, these elements are so super reactive because they all have one valence electron. And because they have one valence electron, we're going to learn about this a little bit later, but when they form compounds or they react with something, they lose one electron, which makes them form a +1 ion. Group 2 are known as my alkaline earth metals. So group 2 is also in my S block, and they are also highly reactive metals. But they're not quite as reactive as group 1. Now, these are also super reactive because they have 2 valence electrons, but where group 1 only has to lose 1 electron to form a compound, these have to lose 2, which means they do form a +2 ion, and they're just slightly less reactive than group 1. So now we move into my biggest group on the periodic table, and that is my transition metals. So I'm not quite sure why this isn't yellow, but the transition metals are this whole group here, and that also includes my 2 rows on the bottom of my periodic table. So my transition metals are my D block and my F block of the periodic table. And the transition metals are kind of weird because they can fit more than 8 electrons in their valence shell. And the transition elements can form more than one type of ion. So what we were just saying here, where these all form +1 and these all form +2, some elements here might form a +2 and a +3, or a +1 or a +2. It just depends on what they're bonded with. My group 17 here, also known as group 7, are my halogens. So my halogens are all nonmetals, and they all have 7 valence electrons. And because they all have 7 and they all really, really, really want 1 more in order to have a full octet, which means 8 valence electrons, they all form a -1 ion. They all gain 1 electron in order to complete their valence shell. Now, because they only need 1, they are our most highly reactive nonmetals. Now, group 18 or group 8 here are my noble gases. So we looked at those a little bit when we were doing noble gas configurations. Now, noble gases have 0 chemical reactivity. Each of these elements has a full valence shell, or an octet. So neon, argon, krypton, xenon, radon all have 8 valence electrons in their outer shell, whereas helium has 2. But because helium only has that first shell of electrons, it is filled with 2. Now, my last 2 groups that we're going to look at are my lanthanide and my actinide series. So these 2 rows on the bottom of the table are part of my F block, and they are categorized as transition metals, but they have their own special names. So they actually fit into this little place right here on the table. And the lanthanide series starts with lanthanium, or lanthanum, however you want to pronounce it. I don't know the right way. And then my actinide series starts with actinium. So they're really easy to figure out which one's which when you're looking at a periodic table. And we're going to work more with the periodic table, the trends, and how our electron configurations fit all into this mess later this week.